Basic Optical Concepts, Unit 2. And here we're going to demonstrate Snell's law, or how light will be bent by materials that are denser than air. It requires that light will strike the surface at an angle. If you envision this to be air and this to be a piece of glass, we'll just use the line to represent the glass. And this light has positioned itself so it strikes the surface of the glass at an angle. If we want to know how that light is going to be bent using Snell's law, what we need to do first of all is at the point of contact we need to draw a perpendicular line. And we're going to extend this line above the surface, in the air, and below. This line is called the normal. The normal is a line drawn perpendicular to a piece of glass at the place the light strikes that glass or plastic. And then we can measure that angle. That angle, let's estimate just by visual representation that that angle is 30 degrees. And they call that the angle of incidence. Incidence meaning it's striking the glass. If that light ray wasn't bent, it would continue straight through, and it's helpful for us to see that on this drawing. And if I draw it correctly, it looks a little bit bigger, but if I draw it correctly, it should be this original path would be 30 degrees if the light was not bent. We know what Snell proved was that when light goes from air, which is less dense, into a material that's denser than air, glass, plastic, water, it is going to be bent. It's going to be bent from its original path. And we'll label this original path, OP. It's either going to be bent away from the normal, or it's going to be pulled towards the normal. And Snell's law says that when light goes from air to a material that's denser than air, like glass, it's always going to be pulled towards the normal. And the only movement it can make is from this original path. So it either has away from the normal or towards the normal. And Snell's law says it's always going to be pulled towards the normal, so in this direction, when it goes from air to something denser than air. So the only thing that I know at this time then is this angle of refraction is less than 30 degrees. Because if it was its original path, it's going to be bent somewhere in here. Now using trigonometry, we can calculate, given this angle, given this index of refraction, using trigonometry I could calculate this angle. That's really not necessary for this course. What I'd like you to know is that it's going to be bent towards the normal and be able to represent that on paper. This is Basic Optical Concepts, Unit 2, Snell's law. And here we have a situation where a light ray is in the piece of glass, and it's going to pass the barrier between the glass and the air. And we want to know, how is this light ray going to be bent once it reaches the air again? So we need to draw the normal, which is at the point of contact. It's a perpendicular to the surface of the glass at the point where the light ray strikes the glass. And again, this is the normal. Now Snell's law says that this light is going to be bent from its original path. So if I draw the original path in here with just a dotted line, let's estimate just visually how many degrees that would be. Let's say this is 20 degrees is the angle of incidence. So that light ray is striking this piece of glass, going to emerge into the air at a 20-degree angle. Snell's law says that it's going to be bent, and when light goes from glass to air, it's going to be bent away from the normal. This would indicate it'd be bent towards the normal, and this would indicate that it would be bent away. And in this case, because of this situation, the light ray is going to be bent away from the normal. So what we can say about this angle is that it's greater. The angle of refraction is greater than 20 degrees. This is Basic Optical Concepts, Unit 2, Prism Calculation Example. Prism in your textbook is defined as a 1 prism diopter lens will deviate light 1 centimeter over a distance of 1 meter. And if you look in your textbook, you'll have a picture that defines this definition of a prism diopter. A prism is a lens that displaces light, it doesn't focus light. And we can calculate, based on how strong the prism is and how far away the prism is from the object, how much deviation there's going to be. We can solve any equation for any of these three unknowns. The other thing that's of interest in this calculation is, notice that each three things has a different unit of measure. That's very odd in algebra. Usually you have to put everything in the same unit of measure, except for the prism calculation. Here we have prism diopters, here we have centimeters of displacement, and here we have meters as the distance of the source to the prism. So here's our problem. We have a 6 prism diopter lens, and it's at 2 meter distance. We want to know how much is the light displaced, or how much light displacement is there. So what we want to do is fill in this relationship with our values and solve for the third. So instead of 1, we're going to put 6 for the prism diopters. And we don't know what the displacement is, that's what we're trying to calculate, so we'll use A. And we do know that we have it at a 2 meter distance. So there's our problem, 6 equals A divided by 2. Another way we can solve this algebraically, but you can also think about what divided into a number will equal 6. This is a fairly simple equation, so you might be able to just think about that intuitively and know what can I divide 2 into to equal 6. Let's solve it algebraically though, where A is divided by 2, so we want to do the opposite of division. We want to multiply both sides of the equation by whatever's in the denominator. So we're going to multiply both sides by 2. And don't forget, you still have that 2 there. So now again, 2 divided by 2 is 1. So now we're left with A equals 6 times 2, or A equals 12. And we pull up and get our units of measure there. So A equals 12 centimeters of deviation.